first let's have a review of what we learned yesterday. So yesterday we mainly talk about first some machine learning algorithms, some commonly used machine learning algorithms like linear regression, like support vector machine, KNN, K-means, decision tree. These machine learning algorithms, and then we spend a lot of time to talk about the deep learning part. So first, we give the definition of what is deep neural network. That is a neural network with a lot of hidden layers. So that's why we call it deep, and it's from the neurons in our brain. That is artificial neurons in our brain, and we use function to simulate the structure of these neurons. And one problem of the perception, here is the example of perception. Here is a single perception. We got a lot of input x1, x1, x2, x2, xn, and we do weighted sum of these input plus we do weighted sum of this input and through an activation function to add the nonlinearity of this perception. But the fact is that the single perception, this perception is just a classifier. It can only solve linear classification problem. So it cannot solve problem like this is XOR problem, because for XOR problem, we need two straight lines in two dimensions to separate these two classes. So the perception failed to solve this XOR problem. And then the scientists proposed some other more complex structure of neural networks like this. We add a lot of hidden layers in the neural networks, and at each hidden layer, we can use a lot of neurons to process information from the last layer. So that is the first two terms, deep neural networks and the perceptrons. And then we spend a lot of time to talk about how to train the model, because the goal of the training process to train the model is to adjust the weights and bias to make the model make a right prediction. So to judge the difference between the actual and the prediction, we will use a loss function. So to train the model, the aim is to find proper weights and bias to minimize the value of the loss function. So for here is an example. We got a model, and this model are used to solve problems like this. The sample only got two features, that is W0 and W1. So we can draw our loss function like this. It's like a mountain. So the goal to train the model is find the minimal value of this loss function, that is to go down to find the value of this global value of this mountain. So that is the purpose to train the model. So how to train the model? We introduced several methods to train the model. So the most commonly used method to train the model, the method we all gonna use is gradient descent. So gradient descent is here is the weight that will be updated, and we will use the gradient. So the gradient of a function represent the steepest direction. The steepest direction, like here, the steepest direction of the function here, that is the trend of the function. So if we follow the opposite, direction of the gradient, so we can go down very, very fast. We can go down very, very fast till to the lowest point of the loss function. So just like we are blind, and now we are dropped anywhere of the mountain, randomly dropped anywhere in the mountain, and we are blind, and we will use our foot to try every direction around us and follow the steepest direction to find the lowest valley, global valley of this mountain. So that is gradient descent. So the function to update weights and bios in neural networks are just like this. Here is the W that will be updated, and here this is the gradient descent, and the minus means the opposite side of the gradient direction, and then we use this function to update the weight and bios parameters in our model. And for gradient descent, we got several strategies to calculate the gradient. The first strategy we call it global gradient descent algorithm. So for global gradient descent algorithm, that means every time we will use all the samples in the training data set to calculate the gradients, to calculate the gradient here. And so for global gradient descent, it is very stable, but it requires a lot of computing power and computing storage. And the next one is stochastic gradient descent. So compared to global gradient descent, stochastic gradient descent would randomly pick, select one sample from the training data to calculate the gradient, and then update the weight and the bios in the model. So this stochastic gradient descent may be not that stable. It will go down to the mountain like it will go down to the mountain like a zigzag here, like this. It's not that stable, but for gradient descent, it may be very, very stable if we always dropped at the same point of this mountain. So the way to find the minimal point of the loss function are always the same, but for stochastic gradient descent, the way to the valley is not that stable. So the third strategy is we use mini batch gradient descent. So here mini batch means every time we will select a group of samples to calculate the gradient at this point, and then update the weights and the bios. So the number of this group of samples, we call it batch size. And in neural networks, batch size always a hyperparameter, and we need to decide the batch size of our model during training process. So usually batch size always, the number of batch size always depend on your computing storage and your computing power. If your computer is very powerful, you may assign your batch size a very large number. Or if your computing power or computing storage is not that sufficient, so the number of your batch size may be roughly smaller, maybe like 8, 16, or 22. So that is gradient descent. And then we talk about the activation functions. So the aim of the activation function is to make the model a nonlinear model. And here, there's several activation functions. The first activation function we introduced is sigmoid function. And here is the sigmoid function. It can map any input to range 0 to 1. So that means the output will be the probability. So sigmoid function always work as a gate function in neural networks. And for task function, it can map any input to from -1 to 1. So for sigmoid function, if our input is greater than 0 or smaller than -0, the derivative of the sigmoid function will be very close to 0. So if the derivative of the sigmoid function is very close to 0, that means the gradient will be very close to 0. If the gradient is very close to 0, that means we cannot update. We cannot update our weights during this training epoch, during this training process. So during this training step, so that means the model will not be improved. The performance of this model will not be improved. And then the task function also, if that is the derivative of this task function. So it has the same problem, but sigmoid function can easily have the gradient validation problem. And here is a variant of task function. We call it soft sign function. And here it's equation. And then we talk about ReLU function. So ReLU function is a very simple, and usually when we build some models related to images, first ReLU function will always be our first choice as activation function in this model. And for the models to process the sequential data, we may first consider about the task function of the variance of the task function. And here is the variance of ReLU function. Actually, ReLU function has a lot of variants, like leaky ReLU, or we can call it P-ReLU, and other variants. But here we just introduced the soft plus function. It's a variant of ReLU function. And so in computer vision, first we need to try maybe ReLU function as an activation function, and for model to process sequential data, first we need to try task function. So that is the activation functions. And the last activation function is activation function usually be used in classification model. And usually we would use softmax function as the output layer of the classification model, and the function or how the softmax function work. The softmax function can always map a k-dimensional vector to another k-dimensional vector, but here the output k-dimensional vector, in the output k-dimensional vector, every element actually represent the probability of the corresponding category of the corresponding class, that is soft function. So that's all for the activation functions. So here are some factors of these activation function. So there are a lot of activation functions you can choose from. But for example, if you want to create your own deep learning models, and you tried these activation function, and these activation function are not that good, so you can try to create your own activation function, but you may consider these factors, but always we would choose from the already existing activation functions. And then we talk about that is the most important part in this training session. We talk about the types of neural networks. So first we introduce the feedforward neural network. So feedforward means the information would only go from the input layer to the output layer. There's no feedback. that is feed-forward. And then we introduced multi-layer, fully connected artificial neural network. So multi-layer means there are a lot of hidden layers. And here, fully, what does this term fully connected mean? So here, fully connected means that every neuron would process information from last layer, will process all the information from last layer. So that is fully connected artificial neural networks. So here is an example. And another, the multi-layer perceptron is also a multi-layer fully connected artificial neural network. Here is an example, a model with 2 hidden layers and 1 input layer and 1 output layer. So that is the first kind of neural networks, that feed-forward neural networks. And then we input spatial feed-forward neural network, and we call it convolutional neural network. So convolutional neural network has a very good, very excellent performance, especially in image processing, because if we use some traditional algorithms to process image, to extract features from the image, we have to design the filters, we have to design the templates manually according to the data set. But the convolutional neural network can automatically extract features from the image. And then we talk about the convolutional neural networks in detail. First, we talk about the structure of CNN. So CNN always contains 3 types of layers. First, we call it convolutional layer. So the purpose of convolutional layer is to extract features from the image. And the second type of layer, we call it pooling layer. So the purpose of pooling layer always is to reduce the size of the image of the feature map. And then the third type of the layer, we call it fully connected layer. So after the output of both convolution layer and pooling layer are all a matrix. For example, the output, here, the output of the convolution layer is a matrix, right? And also the output of fully connected layer is also a matrix. So if we want to do multi-class classification problem, so the fully connected layer can map a matrix into a vector and reduce the dimension of these vectors to the corresponding categories. So that is the 3 types of convolutional layer. And then we talk about how to do convolution calculation on an image. That is how we do convolutional calculation in convolutional layer. So here is an example. Here is an example. We got a 5x5 image, and we got a kernel. This kernel is a 3x3 kernel. So in this kernel, we will do calculation like this. It's also weighted sum. And we do multiplication 9 times, and we add this line number together. Here is 1 output number, and the kernel will scan the entire image. So that is the single kernel convolution calculation. And we also got multi-kernel convolution calculation. That is at the same. Wait a second, maybe I will put down. Sorry. So for CNN, we can CNN and the convolution layer, and for one convolutional layer in one convolutional layer, we can use we can use several kernels. We can use a lot of kernels to extract features from the same image, just like this. We use 2 kernels to extract information from the image. And here, this image is a multi-channel image. That means this image is a color image. So here is the example we've explained, and here are some terms in convolutional layers. First is padding. So padding equal to 1. That means we will add 2 columns and 2 rows, a circle of zeros or circle of zeros around the image. So the aim of padding, use 0 padding, is to why we need the padding. So the aim of the padding of use or pad an image is to extract features at the boundaries of the input image. So we want extract features at the boundaries of the input image. So we need to pad so that we can do weighted sum. We can do weighted sum around these boundaries. That is padding. And so here for stride means equals to 2 means we will do convolutional calculation every 2 pixels. And so the kernel would do convolutional calculation every 2 pixels during a scan the entire image. So that is multi-kernel convolution calculation. So here, one question is that why convolutional calculation can extract information from the image? Why we need convolutional calculation in images? Why it can extract information from the image? So here, I may use an example to explain why convolutional calculation can extract information, extract features from the image. So first, wait a second. First thing is to explain why is features. So why is features? So in an image, features actually means the textures or the outlines of this image. For example, here I will give you an example to understand the features, to understand how humans understand images. Here is an image. Here is an image. So the question is that is it a girl or an old lady in this image? What can you get from this image? It's a girl or an old lady or both?
Both.
Both? Is there anyone can only see a girl in the image?
I can see a girl.
And what about an old lady? Is there anyone can only recognize an old lady from the image?
No.
I think it's the young lady.
Okay, thank you so much. So some of you, that is the same image, but some of you see a girl from the image, some of you see an old lady from the image. So the reason, wait a second, something wrong. So the reason why the same picture, but we extract different objects from the image is about the features and experiments. So how humans understand about image, we understand the image by features we extract from the image and our experiments. So for this image, the features, the key feature of this image maybe here, right? Here, here, and maybe here, and this, and also these textures, and also these textures. So we both extract some key features from the image, the same key feature, from the image. But how we understand about the image is feature plus experience. So here, there are some local features, and we combine these local features together, and someone would view this feature as the eye, and someone would view this local feature as the ear according to your experiments. So if here you view this feature as the eye, and here is the nose, so here is a mouth, so you can see an old lady from the image, right? But the same feature, if you view this feature as the ear of a girl, and here is a chin, and here is her leg, so you can see a young girl from the image. So the same feature plus experiments, combine these two together, and it becomes the understanding of the image. So why we view this part as the feature of the image? Because the feature of the image actually is the edges and the textures of the image. So the edges and the textures, that is the place, the pixels, that is the pixels that the intensity would change dramatically compared to this place, Because, for example, the background are all black. That means the intensity between these samples, the intensity between these pixels doesn't change much, but the intensity between these samples change dramatically, and these are edges and textures. For example, these are edges, like the outline of some objects, and these are textures. It's just some small straight lines, some small curves. That is features and experiments. That is how humans understand images. So we understand image first from features. So we understand image first from features, and from what kind of feature? So from local features. These are local features. And then we will combine, our brain will combine these local features together. It becomes a global feature. That is a global understanding of the image. That is how humans understand images. So here, for convolutional neural networks, it wanna simulate how humans understand about image. That is, you want to extract some local feature and combine this local feature together, it becomes the global understanding of the image. So convolutional operation is a kind of operation that can find the relationship between pixels. For example, here is a checkerboard, and so the arrow labeled A, here is arrow A, here is an arrow B, here is arrow A, here is the arrow B. Actually, arrow A and arrow B are of the identical brightness, because the brightness of arrow, the brightness of A and B are the same. But if we look at this checkerboard, so it seems that A is darker than B. Right? So A is darker than B, right? But actually A and B are the same, has the same brightness. So maybe we can view in this way. Here we just cover some pixels around A and B. Cover some pixels around A and B. A seems still darker than B. Cover some pixels around A and B. A still seems darker than B. Cover some pixels, and they are not the same. As we cover all the pixels around A and B. A and B are the same. They share the same brightness. So the reason why at the first time it seems A is darker than B is because the surrounding pixels. It's because the surrounding pixels, because the surrounding pixels of A is brighter, and the surrounding pixels of B is darker. So how we look at, so how the pixel looks like in our brain, in our eyes, not just depends on the single pixel, but also depends on the pixels around this pixel. So we will use convolutional calculation. So that's the reason why we use convolutional calculation. So we will go back to this slide. So that's the reason why we use convolutional calculation. So we will use convolutional calculation to find the relationship, between these 9 pixels, So we will know how the central pixel actually look like in our eyes. So that is why convolutional calculation can extract features, and the convolutional calculation can find the relationship within several pixels by the weighted sum. So that is convolutional calculation. And then what we're gonna talk about is the main concepts. The main concepts of CNN. So CNN actually got 2 main concepts. So 2 main features. The first feature, we will call it local receptive field. The first feature, we will call it local receptive field. So to understand local receptive field, so just as we mentioned that how human beings understand images, we extract features, local features. First, we extract local features and then combine these local features together. It becomes the global feature, the global understanding of the image. So the CNN want to simulate this mechanism. The CNN want to simulate how human beings understand about images. So, for example, here is an example if we use fully connected neural networks to extract a feature. So for fully connected neural network, every neuron would receive all the information from last layer. That means every neuron would process all the pixels in the input image, right? So that means every neuron will try to find the global information from the image directly. So it will cause 2 problems. The first problem is that so it's not the same as how we understand about image. We understand about image first from local information, but for the first time, the fully connected layer, just one neuron just want to find the global information from the image. So that's impossible. Another disadvantage is that the computation load will be very, very, very large. There will be a lot of hyperparameters. There will be a lot of hyperparameters if we use fully collected layer to process the image directly. So that is a problem. So here we use local receptive field. So why is local receptive field? That means every neural would only focus on several pixels of the image, just like this. Every neural would only focus on several pixels of this image. For example, this neuron may focus on the hair of Einstein, and this neuron may focus on to detect the mouth of Einstein. And then we combine the local information together, it becomes a global information. So that is the same of how human beings understand about images. So how to implement this local receptive field? So in CNN, to implement this local receptive field, we will use much smaller kernel to extract information, to do convolutional operation. We will make the kernel, the size of a kernel that is much smaller than the input image. So for example, our input image is 400 by 400. So usually the size of a kernel may be 3 by 3, 5 by 5, 7 by 7. 7 by 7 is a very large kernel, or we can use 1 by 1 kernel. Yes, please.
Is there a specific procedure to calculate the kernel size? Because it may affect the
size of a kernel. The size of a kernel actually is also a hyperparameter. You need to decide the size of your kernel. It's the size of a kernel is a hyperparameter. And so that is the implementation for local receptive field. And the advantage of this local receptive field concept of materialism is, first, it can reduce the memory requirement, right? Because every kernel would always focus on 9 pixels on the image, and if it's a 3 by 3 kernel. And the second advantage is that it simulates how human beings understand about image from local to global. That is the first concept. And the second concept we're going to discuss is a parameter sharing. So what is parameter sharing? So to explain why is parameter sharing. So first, let's have a view of some example. If we use fully collected layer, right? If we use fully collected layer to process the image, what will be the problem? So here, if we use fully collected layer, so the input of fully collected layer is always a vector, a fixed length vector. So it's always a fixed length vector. So as soon as we convert a matrix into a vector, so the relationship between these pixels would be lost. The spatial in relationship between these pixels will be lost. That is the first problem. And the second problem, maybe we can have a view of this example. Here is the object we want to detect, we want to locate. So here is the object. So for us human beings, no matter how the object shapes on the image, we can always recognize that it is the same object, right? We can always recognize here is the object, here is the object, here is the object. But for the fully collected layer, things are different, because if the location of the object shifts, that means the input vector, the values of the input vector will be changed. The value of this input vector will be changed. That is the first problem. And the second problem, we can have a view of this example. For example, here we got a training data set. Here, this training data set, we got 4 images. We got 4 images, and the first image, the label is true because there is object in this image. And for the rest of these 3 images, the label is false because there is no such object in these 3 images. So if we use the training data set, this kind of training data set to train the model, the problem will be so only this 1, 2, 3, 4, 5, only this 6 pixel, the value of this 6 pixel change. The value of this 6 pixel change, but the other pixels are all white pixel. The other pixels are all white pixel. It stays the same. It's the same in this 4 picture. So only this. Okay, I will enlarge. So only this 6 pixel, the value of this 6 pixel change. So the problem will be that when we train the model, only 6 neural, the value of 6 neural would be adjusted, but other neurals cannot be trained. So that is another problem of feed-forward neural network. So why we talk about this problem? That means, so why we talk about this problem? We talk about this problem because image got a feature, we call it image invariance. That means for us human beings, no matter how the object shaped, how the object rotates, how the size of the object changed, how the illumination of the object changes, we can always recognize it is the same object, but it may be different for neural networks. So especially for fully connected neural networks. So to solve this kind of problem, we're gonna introduce convolutional neural networks. So to solve this kind of problem, the image invariance problem for convolutional neural networks, we will use parameter sharing. So why is parameter sharing? So the implementation of parameter sharing is that every time we will use the kernel with the same parameter. So when the kernel scans the entire image, the parameter of this kernel are always the same. So we will use the same kernel to scan the entire image to make sure that no matter how the face shaped, on the image, we can always detect, okay, here is the face. That is parameter sharing. So the advantage of parameter sharing first is to solve the image invariance problem to implement prediction environments. And the second, it can always reduce the memory requirement, That is the main 2 concepts of convolutional layer. So next, we may have a look of the structure, the architecture of convolutional layer next time. Again, and here we got input layer, and we use convolutional layer to extract features, and then we use pooling layer to reduce the size of the feature map, and followed by convolution layer and pooling layer, convolutional layer, pooling layer, and at last we use fully connected layer to map the matrix into a vector. So here, this is a example of convolution layer. And
why did we use 4 convolutional layers instead of 5 or 1?
So the number of convolutional layers is also a hyperparameter. You need to determine the number of your convolution layers in the CNN in your model. So here is just an example. We use 4 convolutional layers. And next, we may have a view just as we mentioned that at the same convolution layer, we can use a lot of kernels to extract a feature. For example, here is input 22 by 32 by 32 by 3, and here we use six convolution layer. We use six kernels, and the size of each kernel is 5 by 5. And here 3 means the 3 channel of the image, and we use 6 kernel to extract features of the image. So here the output, the number of the output feature would always be 6. So there will be 6 feature maps. There will be 6 feature maps. And why we use several kernels to extract the image for at the same convolution layer? Because maybe we want to fully extract the information from the image, so we use several kernels at the same time. So maybe each kernel may represent to detect a part of the information from the image. Maybe the first kernel are responsible to detect the edges of the image, and the second kernel are responsible to detect some curves from the image, or some small triangle, or some small corner of this image. So that's the reason why we use several kernels to extract the same
It means
image.
that more kernels will improve feature extraction of the CNN.
Yeah, but also the size of your kernel at the same layer is also a hyperparameter. You need to decide, but there are some principles. So I will explain maybe in the image classification hands-on practice. So if we use a lot of kernel, if we use so many kernels for the same convolutional layer, it will requires a lot of computing power and a lot of computing storage, and maybe the features of the image only maybe got 10 categories of the 10 categories, like the color of the image, like the curve of the image, like some straight line of the image. But now we use 1,000 kernel to extract the feature from the image. So a lot of the features from this 1,000 image are very similar. So it's also a trade-off. You need to determine the number of your kernels, and the size of the kernel also is a hyperparameter. And maybe here we can have a view of how the feature map looks like, after convolutional layer. So here, this picture, we call it is a feature hierarchy. It's a feature hierarchy. So for example, here is the input image. So after the first convolutional layer, it can only extract some features like straight lines. But after the second convolution layer, it can extract some features like curves. And when we continue to add the number of convolution layers, it can extract some partial features like the nose, the eyes of one person, the ears of the object, of the face. And then when we continue to increase the number of convolution layer, we can extract the entire image. We can extract the entire object of the entire object in the image. So let's have a look of an example. For that is the effect after the first convolutional layer, only straight lines. So after the second convolution layer,
I wanted
yes,
to
please.
ask that you mean to say that the size of the kernel, the number of these kernels, and the number of the layers in the convolutional neural network depends from image to image, or from neural network to neural network? Like these parameters are defined based on the input images, or are they defined on the basis of what kind of neural network, or what kind of how many number of layers you are using in the convolution neural network?
There is no rule to determine. It's determining on what kind of task you want to solve. It depends on your data set, and also it depends on the output. There is a lot of facts that can affect these hyperparameters, like the number of convolution layers, the number of kernels, and the size of the kernels. So there is no such function, or there's no such principles to tell us the exact number of the convolution layers, the exact number of the size of kernels. For example, for this image classification program, I can use a model with maybe 20 convolution layers, and the accuracy maybe is 90%. And now I will try a model with maybe 22 convolution layers. So the accuracy may be 88. So that is an example. So no one could tell us the exactly number of these hyperparameters. So always we will use the model. We will use the model that already have some successful performance on specific data set. We will always try this model that have already succeed, and that is the hyperparameter in convolution layer. You need to decide, and it depends on your model, it depends on your data set, it depends on your task you want to solve. But here is the rule: if you add a lot of convolution layer, so at the first several convolution layer, you can only extract features like these partial features. And if we continue to add the number of convolution layer, we can extract the entire features. But if we continue to add more and more convolution layers, the details of the image will be lost. So if you want to detect some small object in the image, you will not. I suggest you don't use model with too many convolution layer, because the output, because these small features will be filtered out after a lot of convolutional calculation. So that is the trend. We can only tell you the trend if you add the number of convolution layers, but there's no exact number. There's no exact rule to tell us the number of convolution layers we should use.
What if we tell the CNN that we need the eye feature? We will see
feature?
only the eye feature. We predefine the feature we want.
You mean you want to detect the eye of?
Yes.
If you want to detect the eye, you
or classify the image by the eye.
If you want to classify the image by the eye, or if you want to detect the eye of a face, first you need to collect a lot of samples, a lot of faces, the eyes image, a lot of eye image, and use this eye image to train the model. Then the model know, okay, here what you want me do is to detect the eye. You cannot tell the exact. If you want to tell the model to detect the eye, you need to collect a lot of eye images and use these eye images to train the model. So we will continue to talk about the feature hierarchy. So first, here is a fact. After the second convolution layer, we can extract some curves from the image. And as we continue to add the number of convolution layers, we can extract some partial feature, that is some outline of the object. And if we continue to increase the number of convolutional layers, we can extract the entire face of the object. So that is the feature hierarchy. So, but here it will lose information, like it will lose some details. It will lose some details if we use too many convolution layers. So next type of layer in CNN we may use as pooling layer. So the purpose of pooling layer actually is to reduce the size of the feature map, because image contains a lot of information, and the size of image for especially for a high resolution image, there is a lot of pixels. There are a lot of pixels, and the computational load will be very, very, very large. So we need to reduce the size and to reduce the computational load. And here is an example. If the size of the feature map after the convolution layer is 216 by 200, so if we use pooling layer, if we put this feature map into a pooling layer, so that is the output. That is the output of the pooling layer. So we reduce the size. We reduce the size to 130 by 100. So reduce the size by half. Reduce the size by half. But we can still recognize the main feature. We can still recognize the main feature from the image. Like this, here is a car. Here is a car, and here is a road. So that's the reason why we can use pooling layers. Although we reduce the size of the feature map, but we still can recognize the key features from the image. So usually in the pooling layer, we will use max pooling or min pooling. We will use max pooling or min pooling to do pooling operation. So here is an example of max pooling. So for max pooling, always we got a kernel. So always we got a kernel. For example, this is maybe a 2x2 kernel. This is a 2x2 kernel. And so it's a 2x2 matrix. So here within this 4 yellow pixels, if this is max pooling, I will pick up the maximum map value, that is 5 within these 4 pixels. And here strike equal to 2, that means we will do max pooling every 2 pixels. We will do max pooling every 2 pixels. So the size will move to here. The kernel will move to here. So then we will pick the maximum value within this 4 gray pixels, and that is 7, and the maximum value, that is 4, and the maximum value, that is 8. So we do reduce the size of the image from 4x4 to 2x2. So that is max pooling. If it's average pooling, we just take the average value of these 4 pixels. And the next one is fully connected layer. So for fully connected layer, the aim of fully connected layer is to map the matrix.
Excuse me, this pooling layer is a part of CNN at the input side, or is the part of the CNN architecture basically?
It's a part of the CNN architecture basically, just like
right.
this. Okay. And CNN always followed. So always we use convolution layer, and CNN always the next layer of convolution layer, just like this. Convolution layer followed by pooling layer, convolution layer followed by pooling layer, and we can use convolution layer, pooling layer. So pooling layer always the next layer of convolution layer. So it's always followed by the convolution layer. Follow the convolution layer. Yeah. So here the last, yes, here is the last type of layer in CNN is fully connected layer. So the function of fully connected, purpose of fully connected layer is to map the feature map into a vector, like this, and then we reduce the dimension of the vector from around 3,000 to 10. So here, this 10 means 10 categories, for our image classification problem. So here is the overview of convolution layer. Here is the overview of convolution layer. We got input layer, we got convolution layer, we got pooling layer, fully connected layer, and then finally the output layer. So we may have 10 minutes break, and then we're gonna continue to talk about another type of neural networks, that is recurrent neural network. So 10-minute break.
I have a couple of questions. Can I ask before?
Yes, please.
How does we can be so sure that max pooling may extract features and don't lose information?
Okay, your question is how max pooling can extract features of the image, right?
Information is not lost.
Information is not lost. Some of the detail of the image are lost, but the key feature of the image are not lost. So maybe here we can have a view of this example. So that is our input image. We got 3 input image. So here is the object we want to detect, right? Here is the object. And here we use this convolutional kernel to do convolutional operation on this image. And here is output. It's a 2x2 matrix. And after the convolution layer, if we use a max pooling layer and 2x2 max pooling, so within this 2 pixel, we will pick up the largest value 5 from these 4 pixels. Largest value also 5. Largest value also 5. So the output of the max pooling layer are all 5. That means there is object in this image. There are objects in this image. So we pick up the key feature, that is the maximum value of the feature map. We keep
got it.
Key feature, but some details.
There's another question.
Yes, please.
Can we use convolutional layer, then max pooling, and then some other classifier rather than artificial neural network? Like we can use another classifier.
You mean you use convolutional layer and then max pooling, and then we use other classifier?
Yeah, exactly.
Like maybe boosting, ADA boost or SM. Yes, of course you can use, because actually the purpose of convolutional layer of CNN is to extract features. So we can map this image. So for an image is not structured data. So we can map the image, the matrix, into a vector, and then we can encode the vector into some other classifiers like SVM or AWS. You can do it. It can try. There are some algorithms use this kind of architecture.
Okay.
Other question? Any other question? Okay, we may have some rest. We may continue to talk about the neural networks, and before we talk about the recurrent neural networks, first, just a brief summary of convolutional neural networks. So first, the purpose of training a CNN model actually is to find the proper value of the coefficients in kernels, in convolution kernels. So the purpose to train a CNN model is to find the current coefficients in these kernels, in the convolutional kernels. So before we training these coefficients, the coefficients in these kernels are randomly initialized, and then during the training process, we trying to find the proper value to train the kernel, also to minimize the loss function. And so there are some other parameters we need to train. That means the second example is here in fully connected layer, there are also weights and bias. So we also need to find the proper value of these weights and bias in fully connected layer. So that is the purpose of training a model, not training a model, training a CNN model. The main purpose is to find the coefficients in this kernel. And the second key point is that hyperparameters, I just gave an example of hyperparameters in convolutional layers. So in convolutional layers, we talk about a lot of terms, y is kernel, y is height, y is stride, y is and the feature hierarchy. So the size of the kernel, you use 1 by 1 or 3 by 3 or 5 by 5. It's a hyperparameter. It's a hyperparameter. And also the number of kernels in one convolution layer, that's also a hyperparameter. Maybe you can choose from maybe 22 or also 16, not 22, 32 or 16.4 or 124 or 256 and so on. And also the number of convolution layers, how many convolution layers in your CNN model, it's also a hyperparameter. And also padding. If you want to use padding strategy or not, pad or not, it's a hyperparameter. And also the number, the size, the number of your stride, stride equal to 1 or stride equal to 2 or stride equal to 3, it's also a hyperparameter. So you have to decide, you have to determine these hyperparameters. It cannot be learned during the training process, usually. So that is the convolutional neural network. And then we're gonna continue to talk about maybe the last type of neural network. We call it recurrent neural network. So for convolutional neural network, we always talk about the spatial relationship between pixels, and we never mentioned about time, right? We never mentioned about time, but there are a lot of sequential data. In our life. So here we need a type of neural network that can process sequential data, that can process the data according to time. So here is an example of recurrent neural network. So for recurrent neural network, unlike CNN, it's not a feed-forward neural network anymore. It's a feedback neural network because the neural not only transfer from the input to the output, it have a feedback route. That means, for example, if we unfold this neural, this is just one neural, right? The neural would receive information from last layer, and the information of this neural will be transferred to the next layer, to the next neural. And so if we unfold this neural, we will find this neural may look different at different time steps. So here we got a term that is time. We mentioned about time. So this neural looks different at different time steps. Here, this is this neural is at time step t, that is t, and this is a neural at time step t minus 1. This is a neural at time step t plus 1. So for every neural, for example, this neural at time step t, it would receive the input. It will receive the input at this time step. So this is the input at this time step, like xt, and also it would receive the input from last time step. So here, for this neural at time step t, it got two inputs. The first is xt, and the second is from last time step. So also for this neural, it has two outputs. It has two output paths. One would, the information will be given to the next time step, and then the second path, it will be given to next layer. So that is the recurrent neural network. It's just example for one neural. It's just an example for one neural. If we connect a lot of neurons together, it will be looks like this. So there are different types of recurrent neural networks. So different connections. So the first example will be like this. We call it 1-to-1. So Y is 1-to-1. For example, here we want to process the, I will show you. So for RNN, the example 1-to-1 is that maybe for RNN can also solve image classification problem. It can also solve image classification problem. That is 1-to-1, one image as input, and the output is the class of this image. And the second type of RNN, we will call it 1-to-many. That is one input, and there will be many outputs. So the example of 1-to-many maybe is music composition, right? As music composition, and we may input jazz, we may input hip hop, we may input R&B, and the output is a sequential data as a song or something else. Here is music composition. Music composing, or that is 1-to-many. And the third type of recurrent neural network, that is many-to-one. that means we got many input and the output will be only one. So the example of mailing to one maybe the typical example of mailing to one. Maybe action prediction. Yeah. Action prediction in videos, action prediction or motion prediction in videos. So we can divide a video into several frames according to time steps, and we input these frames into the RNN and get one prediction. That is the action prediction of the person in the video. Or like sentiment classification, we input a sentence, and the output is the sentiment analysis. So the third type, wait a second. 1, 2, 3, 4. This is many to one, and the fourth type and five type are both many to many, but here, this many to many example, maybe machine translation. Maybe machine translation, we input a sentence in Chinese and translate this sentence into English. That is many to many. And the second many to many, maybe named entity recognition. That is many to many named entity recognition. So named entity recognition is we input a sentence and to find the name entities in this sentence, if it's a named entity or not in this sentence. Like if this word is a name of a company or not. For example, this word apple, it can be a kind of fruit, and it can be a name of a company. So named entity recognition is to recognize the named entities from the sentence. So that is example. That is types of recurrent neural networks. And here is the structure of the recurrent neural networks. It can process some sequential data. And one big disadvantage of recurrent neural networks is that it will have validation gradient problem. For example, here this neural, if this neural contains a lot of time step, the first second, the first time step, the second time step, the third time step to time step 100. So when we do back propagation to update the weights and the BIOS, so the weights and the BIOS will be transferred from the 1000 or 100 time step and generally to the first time step by plus. So you will find equations by like a lot of values times together. The weights times the derivative of the activation function, and then so maybe that is an arrow. So that is an arrow at time step 100, and we back propagate the arrow by the weights times the weights. Okay, here is a weight. Here is a weight times the derivative of activation function to the time step from 100 time step 100 to time step 99, and then the weight times the derivative of activation function to 90 to 98 time step, and then a lot of them. So there are a lot of values times together. So if one of these value is very small, for example, if this value equal to 0.1 and this value equal to 0.1 and times together, the final arrow turn will be very, very slow. That is, so if the arrow turn is very, very slow, the gradient is very, very slow. So there is we cannot make improvement. The model cannot make improvement during the gradient during the training process. So that is a problem of one of the big problem of recurrent neural network. So here, compared to the vanilla neural networks, there are variants of recurrent neural network. So the typical example is LSTM. So a typical example is LSTM. So for recurrent neural networks, it's just like a human that remembers everything from the past. It remembers everything. So there is too many rubbish. In my brain if I remember everything, because some of them are not important, some of them are important. So here we introduced another type of RNN. We call it LSTM, that is non-short-term memory. So this is a structure that can help us to drop some rubbish and just leave some useful information, useful experiments in our brain. That is long-short-term memory. This is the structure of long-short-term memory. So for long-short-term memory, so for LSTM, we got the three gates. We got three gates. One is a forget gate. So the forget gate would receive the information from last time step, that is HT-1, and also the information that's at the input of this time step XT. So then through
show the screen. Can you please show the screen?
Oh,
sorry.
Kindly show the screen.
Oh, sorry.
Show the slide, please.
Okay. Here for LSTM, in LSTM, there are three gates. One is the forget gate, and the second is input gate, and the third one is the output gate. So the function of this gate is to control what kind of information should be forgot, what kind of information should be input, and what kind of information should be the output at this time step. So for example, here this is the input gate. And the input gate will receive information from the last time step, that is HT-1, and it will receive information that is XT, that is the input of this time step, and it will consider which part of information should be forgot, and we'll use a sigmoid function. So after the sigmoid function, the output will be a probability. The output of will be the probability. So the HT-1 and XT will decide the probability to be forgot, and the left will be add into the cell. So here this line represent the cell. So the cell just like a container that it stores all the experiments leave all the experiments at time step t, all the useful experiments at time step t, So here, forget gate controls how the controls the which part of information should be forgot, and that is a forget gate. And for the input gate, so it's still for the input gate, it's still a sigmoid function. So output will be the probability. So the output will be the probability. So if we don't use the input gate, the original input should be also ht minus 1 and xt, right? Two input. But here we add a input gate. So here it, the input gate, actually is a probability, is a value from 0 to 1, is a value from 0 to 1. So the input gate would also control how many information should be remembered, what kind of information should be remembered, or how many information should be remembered. And then this information will be added to the cell. This information would be added to a cell. So this CT is the new information. And times by the input gate. So this is a gate, new information times by the input gate. And this CT minus 1 is the experiments, is a memory from last time step, that is time step t minus 1. So here, how many memories should be kept is controlled by the forget gate. So that is, this forget gate is also the probability. So we should add these two together and becomes the memory at this time step. So that is the forget gate and the input gate, and the output gate. The output gate also controls what kind of output, how many information should be output for this time step at this time step. Also, it's we use a sigmoid function, as we just mentioned, that sigmoid function usually work as a gate function. So you will map any input to the interval 0 to 1, like a probability. So here is output. Here is an out gate. It controls how many information should be output at this time step. That is the three gates in long short-term memory. So that is long short-term memory LSTM. It got 3 gates, and it's a kind of structure that can remember some useful information and forgot some information that will not bring, forgot some useless informations. So that is LSTM. So that is the types of neural networks. And the next what we're going to talk about is the regularization. What we're going to talk about is regularization. So first thing is, what is regularization? So in machine learning or deep learning, always practitioners would always be afraid of overfitting problem. So we would be very, very afraid of overfitting problem, because especially for deep learning, the models are too complex. It contains billions of parameters. It can be overfitted very, very, very easily. So we are afraid of overfitting problems, and So again, to explain why is overfitting. Overfitting means that your model predicts very well on the training data set, but it got a very bad performance in the real world, in the new data, the model have never seen before. So here, if you meet the overfitting problem, your model is overfitted, you may need to use the regularization to adjust your model. So there are several types regularization strategies. So the first is to add constraints to your loss function, such as L1 or L2 norms. So the second maybe that is data augmentation. So the second one is data augmentation. You need to increase your size of your data set, and the third one is dropout. So first, let's have a look of the L1 and L2 norm. So for the loss function, this is the original loss function. So here, for regularization, we can add some constraints followed by your loss function, like these functions. We use a L2, so we use a L2 norm. L2 norm. So usually we call L2 norm. We call L2 regularization not lasso, but range regression, or we call it range. And for L1, we will call it lasso. So for L1, I will make notes. We call it lasso, and for L2, we will call it range DGE. So first, let's have a view of what is L1 or what is L2. So for L1, we would add the absolute value of absolute value of magnitude absolute value magnitude of coefficients. So we will use this absolute value magnitude as the penalty term. And for L2, we would just use the squared magnitude of coefficients as penalty term. So here, let's have some example. This is an example of L1 regularization. So we add the absolute value magnitude of these parameters. And here is an example of L2 regularization. So what is the difference between L1 and L2 regularization? So for L1 regularization, it will shrink less important features coefficient to 0. It will shrink these to 0. So that is, I will make notes, and I will explain later. So for L2 regularization, it will not shrink. It will not make the less important features coefficient to 0, but very close to 0. So for L1 regeneration, we can use real L1 regeneration to remove some unimportant features together. But for L2 regeneration, this coefficient will not be 0, but some of them will be very close to 0. And here is these two figures shows this is L1 regeneration, and this is the L2 constraint. So for example, here is the value of our loss function. So the mountain, the eye view, the bird view of the mountain, and we convert the mountain into from 3 dimensions to 2 dimensions. So here is a bird view of the mountain. And if your loss function, the value of the loss function are here, that means the loss function is very large. So our aim is to minimize the loss function. So the loss function should be, if the loss function is here, the value of the loss function located here, it means the value of these loss function are very small. So the central point means the value of the loss function is equal to 0. That is the lowest point. So that is our aim. That is our aim. But here we add constraint. So the overfitting means that the value of the loss function in training data set is very, very small, very small, equal to 0. So to make it larger than 0, to make it not equal to 0, so we will add the constraint, L1 constraint. So here, L1 constraint to let the value of the loss function locate within this area. So the loss function will be not that small. So that is the same for L2 constraint. So we will let the value of the loss function locate within this arrow. So the value of the loss function will not be that small. So we can solve the overfitting problem. So that is L1 and L2 constraint, and another strategy to overcome the regularization in deep learning is we can do dataset augmentation. To increase the size of your dataset. And the second type of regularization is we can use dropout. So what is the meaning of dropout? So dropout means, for example, I will show this blackboard. Clear wall. For example, at this convolution layer, there are a lot of neurons. Maybe 10,000 neurons. So there's a lot of parameters. So it will cause overfitting problem. And dropout is a strategy to randomly make some of these neurons dead. So this neural would not work. Randomly pick some of these neural and make this neural dead. So that is dropout. So there will be not so many parameters. So that is regularization in deep learning. And the last section in deep learning overview we're going to talk about is optimizer. So just as we mentioned, there are some strategies like SGD, stochastic gradient descent, global gradient descent, and mini batch gradient descent to update the weights and bias for our model. But there may be some problems. Maybe for example, I will clear all. This is a mountain. For example, this is a mountain, right? okay, the value of the loss function. First, we are randomly dropped here. We are randomly dropped here, and we take step by step, step by step, step by step, step by step, trying to find the minimum value, global minimum value of the loss function. But we may look here, because at this point, it's very flat. This very flat arrow, that's a very flat arrow. So at this point, the gradient distance always equal to 0. The gradient always equal to 0. So we cannot update. So we cannot update the model anymore. So we are locked here. We are locked here. But the global minimum is here. So we may need another strategies to other optimizers, other kinds of optimizers to update our weight and bias to train our model. So the first kind of optimizer we're gonna introduce, we call it momentum. So why is momentum optimizer? So momentum optimizer would, I will write down here, would use a momentum term, that is, it will accumulate the gradient of the past step. It will accumulate the gradient of the past step, like here. If the last step, the gradient is very large, so this step, I will take a larger step. And I will take a larger step, even though the gradient here equal to 0, but I will take a larger step and jump out of the local minimum. So that is momentum. So it could help us to jump out of the local minimum. It will help us to go through the flat. It will help us to jump out of the local minimum. It can remember, it can accumulate, sorry. I hope so for momentum, it could accumulate the gradient of the past state steps. It can accumulate the gradient of the past steps. So it will take, if it's a very, it'll help us to go down the hill. It'll help us to go down the hill faster and faster on the way. It can push the ball down the hill. It can push the ball down the hill and accumulate the momentum turn, and help the ball go down faster and faster, so it can jump out of the local minimum. But the disadvantage of the momentum is that the ball, here is a ball, the ball go down the hill, just mindly follow the gradient of the past step. It manually follow the gradient of the past step. It manually follow the slope. It will be very unsatisfactory, or it will be very dangerous sometimes. For example, if here the steps are like this, and it take a larger step, and they take a larger step, and then according to the momentum, it take a larger step to here, and it take a larger step, and it take a larger step, so it will miss the global minimum, and it will do like zigzag. The route will be a zigzag. It's very dangerous. So here we will introduce another type of optimizer, and we call it add-on optimizer. So here, this add-on means adaptive moment estimation. Adaptive moment estimation, and add-on is properly the optimizer that performs the based on average. So it's properly the optimizer that performs the based on average. So maybe if you create your deep learning model, you can try add-on optimizer first. So for momentum optimizer, it can change a gradient, the gradient according to the gradient of the past step. So add-on optimizer can also change the gradient according to the past step, but it can also change the learning rate. So for momentum optimizer, the learning rate is a fixed value. The learning rate means how long of our foot, and it depends on it's a hyperparameter. It's a hyperparameter, and it's a hyperparameter. So the momentum learning rate is a fixed value, but add-on this kind of optimizer can change the number of the value of learning rate according to the dimensions. Maybe here, maybe I will give some example. For deep learning models, the data we are using contains a lot of features, maybe 10,000 features or more. But the problem is that the gradient follow different direction, follow different dimension, follow different features, maybe variance. Maybe for feature one, the gradient of feature one is very large. Is very large. So for features with large gradient, we may need very small. We may need very small learning rate, right? And for features, maybe for example, feature 2, the gradient of feature 2 is very small. So here we need large learning rate to do gradient descent to find the optimal value of weight and bias to minimize the loss function. So here we need small. So for feature 2, the gradient is very small. So we need large learning rate. So here, small learning rate is required and large learning rate is required. So for momentum, it cannot adjust the learning rate according to different dimension, according to different features. So, but here, if we use add-on as a optimizer, add-on as a kind of optimizer, it can change, it can adjust the learning rate according to each dimension. So maybe we can have a view. So that is the equations for add-on optimizer. It can adjust its gradient at this time step according to the gradient of the past time step, and it can also adjust adjust the gradient. It can also adjust the learning rate. Here, it can also adjust the learning rate according to each dimension. If this dimension have a very large, its if this dimension have a very large gradient, we may prefer smaller learning rate. So that is Adam optimizer. So it's a optimizer that performs the best on average. Here is an example. So if we don't use Adam optimizer, we use momentum optimizer or stochastic gradient descent, such kind of optimizer. So the learning rate is a fixed value. So here, the global minimum. So the global minimum is here. The global minimum is here. Now we are here. If the learning rate is fixed and our foot may be very long, and it will update. It will go like this from here to here to here to here to here to here. It cannot go down to the valley. So if we use the add-on optimizer, it will adjust the learning rate. Maybe you will notice that here the learning rate is too large. It will adjust the learning rate to a little bit small, so we can go down to the valley to the global minimum. That is the optimizer. Actually, there are lots of optimizers. We just introduced two optimizers. So that's all for the deep learning overview part. Let's have a review. Although we don't have, maybe the time is very limited. And first we talk about neural networks and the definition of deep neural networks. As a kind of neural network with a lot of hidden layer, and we talk about the single perceptron. Single perceptron is actually a linear classifier, so it cannot solve XOR problem. And so we can add a lot of hidden layers, or we can add a lot of neurons in one hidden layers to make the single perceptron into a multi-layer perceptron. And then we talk about how to train the model. We use gradient descent to train the model. We use backpropagation. When you use backpropagation to backpropagate the arrow from the output to each neuron and to calculate how many responsibility this neuron have to take for the arrow. So that is a training rule, and then we talk about activation functions, and then we move to the types of neural networks. We talk about the feed-forward neural network, multi-layer perceptrons, and convolutional neural networks, and recurrent neural networks. And then we talk about regularizations as a kind of algorithm or strategies to overcome the overfitting problems in deep learning. And then we talk about two types of optimizers. The first one is momentum. It's a kind of optimizer that can accumulate the gradient of the path step, so we can go down the hill faster and faster. And another type of optimizer we mentioned about is the add-on optimizer. This kind of optimizer cannot only adjust the gradient according to the path step, but it can also adjust the learning rate according to each dimension. So the dimensions with large gradient would have a roughly small learning rate. So the features with small gradient would have a large learning rate. That is optimizer. And here are some applications of deep learning. For example, image classification and scene recognition, whether it's a kitchen or a bathroom, and face detection and object detection, semantic segmentation, or like this, and style transfer, and super resolution to convert an image with low resolution into an image very with very high resolution and optical character recognition, and some applications of natural language processing, machine translation, sentiment analysis, and some example, some application in speech processing, speech recognition, and so on. So that's all for this chapter. So we may move to the hands-on practice very quickly, and so let's have a view of the hands-on practice. So that is the final part. That is the last part of the whole training session. So in this hands-on practice, our goal, what is our goal? Our goal is to create an image classification model. So first thing we're going to do is we're going to explore our dataset to look at how the dataset looks like. Wait a second. I'm going to show you the dataset. So here, just forget some Chinese characters. We need to focus on these 5 folders. So we need to focus on the 5 folders. So for this image classification model, what we're going to do is to create a model to recognize these 5 classes, these 5 types of flowers. First one is daisy. So if we open this daisy folder, we'll find a lot of images related to daisy, a lot of daisy images. And the second one is Z9. So if we open this Z9 folder, we found a lot of Z9 images. And the third one is roses. And here are a lot of rose images. And the fourth one is sunflowers. And the last one is tulips. So that is our goal, to do image classification, use deep learning model and TensorFlow. So the first step, we need to import some module. Here, this module, that is scikit image module. That is a module to process image, to resize image, to array images from our system, from the folder. So first, if you haven't installed this scikit image, please install. You can install this scikit image, this sk image by this command, and run it. So that is the folder. That is the modules we need to install, and then what we're going to do is to see here is some path and model name. So first we need to identify where is our data. So our data is here in flower photos. I've already sent you guys the data set and also the Jupyter files, and you can open it, have a look at these Jupyter files, or you can open it and practice trying to run this code. So here the model's path is the directory to save the model. That is a directory to save the model. And the name of the model, also the name of the model. When we are satisfied with the performance of the model, we need to save the model. So here is the name of the model we're gonna save. And next thing we're going to do is for images, for images, we have look at these images. So the size of the image varies. So the size of this image varies. So here we need to scale this image. We need to scale this image. So we need to resize the input images to the fixed size, that is 100 by 100 by 3. Here 3 means 3 channels. So it's a color image. So then the first task we're going to do actually is to read the image into the memory, read the image into memory. Here we define a function. We call it read images. We define this function, and then we will use OS. So OS is a module. So OS is a module to interact with our operating system. So we can use OS to get the list of the directory of certain parts. So first, for example, here, the function of this part is to get the list of directory under this path. Maybe we can have a look. So under the flower photos directory, under this folder, we can find 1, 2, 3, 4, 5 directories, 5 folders. And then here, this if statement is to check if the path plus x, if the sunflower photos daisy exists or not. If it exists, so it will do path plus x. So the output of cat will be like this. So the cat, this list, every element actually is the address, is a directory of each category photos, like this. So flower photos, daisy, flower photos, dandelion, flower photos, roses, flower photos, sunflowers. So then the next subtask we're going to do is go inside this folder. For example, first we go inside this folder. So we're here, we use enumerate. Sorry. Enumerate. We use enumerate to get the index. So the index and the value of the elements. So first the index equal to 0 and the folder equal to flower photos daisy, and then we go inside this folder and use this for loop to read every image in this folder. So here we use globe this module to read every JPG image in this folder. And then for every image, first we read the image. Use IO read. Here IO is a function from the SK image. We use IO read image equal to image, and then we resize the image. We use transform resize. Transform also from SK image. We use transform resize image and resize the image to 100 by 100. So the output image will be 100 by 100 by 3. And then we append the newly readed image into the list we created. So here, these images list means would store all the images, and here this list label would store the labels of this image. So we add the image sample into the images list, and then we add the index. So here, this for Daisy, the index is 0. We add 0 into the label. So for Daisy, its label is 0, and for that night the label is 1, and for roses the label is 2, and for sunflowers the label is 3, and for tulips the label is 4. So that is the process to read the image. So we can have a view of the return values. So for the return values, first we need to return the images list. That is all the samples. So then what we're going to do is to convert the data type into float 22. And then we also need to return the labels. We also need to return the labels of this image. That is the labels list, and convert the data type into int22, because labels are int 0, 1, 2, 3, 4. And then we call this function read image function. We call this read image function to read all the image. So this data contains all the information about these images, and this label contains all the labeled actual label. So then we can print the data shape and the label shape. Here, the data is around 3,670. So that means there are 3,670 images, and every image size is 100 by 100 by 3. And the label, the size of the label, the shape of the label is also.
Can you tell us that what does 3 represent?
You mean 3? Okay.
Yeah.
3 means present the channels of the image. Just like we mentioned for a RGB image.
Yeah,
so,
okay, got it.
Okay, thank you. Okay, here for labels, every image got a corresponding label. So the shape of the labels equal to the number of images. And for the next cell, so the next task is we need to separate these images into training dataset and also into validation dataset. Into validation dataset, because during the training process we need training dataset and validation dataset. So I will not to explain this code step by step, because these are very simple code. So the ratio of the training dataset and the validation dataset, here we see the ratio equal to 1.8. So that is 80% of the images are training the samples, and another 20% are the validation samples. So that is data pre-processing task. We read the data, we resize the data, we read the data from these folders, and we resize this data. We add the information to the list, we add the label to the list, and we split all the samples into training samples and the validation samples. So the next task we're going to do is to create our model, to create our neural networks. So here we're going to create a convolutional neural networks for image classification model. So as we mentioned, for TensorFlow, always the input and output will be a placeholder. So here the input is a placeholder, and what we're going to do is to input the images in the placeholder. So the shape of the placeholder here, long means any shape, any shape. So the first long actually means the size of the, not the size, number of the images, and the WH is and C channel. WHC is 100 by 100 by C. So here, what we're gonna input, maybe like 32 by 100 by 100 by 3. That means we would input 32 images, and each image size is 100 by 100 by 3. And the name of this placeholder is X, and the data type is float22. And for this folder, for this placeholder, Y is the output. That is a prediction. So that is a prediction of the model. That is the predicted label of this image. So here, the shape is none. Also, if we input 32 images, so the output should be 32 ints. And the name is Y under 9, and the data type is int22. And here,
why is data type 32?
Y data type is 32 or int32. Because our label is maybe 0, 1, 2, 3, 4. So here we make the default value of the prediction into int32. Because maybe for Daisy, its label actually is 0, the label is 1, the label is 2, the label is 3, the label is 4. And for the 32 and the float 32 and int32, for TensorFlow, the default value, if you don't identify the default value of the placeholder of the constant, so you will get a default value that is float 32. So if you don't identify the data type will be float 32. So here we use int32. And then, yes, please.
Yeah, I have a question. This code is in TensorFlow, right? I want to ask that in our exam, can we use a high-level library like Keras? Keras, which is built on top of TensorFlow. Can we do a task in Keras?
You can use Keras in the lab exam. Yes.
Oh, okay, thank you.
Okay, thank you. So here in this function, we call it inference this function. So this function is a process to create our CNN model, So let's have a look. So the parameters for, of course, input tensor, that is input samples, and the train means if you want to train the model or not. So the train can be false, can be true, and the regularizer, that is the parameter for regularization. If you want to add regularizations or not. Here, the first TF variable scope, within this wait statement, we would add our first convolutional neural networks. For example, in our convolutional neural networks, we got a filter. So the filter always with weights and bias. So weights means the coefficients in the filter, and every filter got a bias. So here, first we need to define our weights. So these weights are bias, are parameters we need to train during the training process. So we define the weights and BIOS as variables. So here we use tf.get variable. So the name of this conven1 weights, the name is weights. And first, we can have a look of here. The size of the weights here equal to 5 by 5 by 3 by 22. So here, this 5 by 5 actually is the size. 5 by 5 by 3 is the size. 5 by 5 by 3 is the size of our kernel, right? It's the size of our kernel. And here, 32, sorry. And here, 32 actually is the number of the kernel in the first convolution layer. So usually we use a vector with 4 elements. We use a vector of 4 elements to indicate the size of the weights. First 2 means the weight and the height, the weight and the height of the kernel, and the second and the third value means the channel of the weights. So the channel actually equal to the channel of the input image. So here the input image got 3 channels. So the channel of the weights need to be 3. And this 32 means here we use 32 images to extract features from the input image. So here the second one is the initializer. We use normal initializer. When you use normal initializer to initialize the value of weights. And the next is BIOS. So we define BIOS also as variables, and the name of BIOS is BIOS. And here, what does this 32 mean? Any idea? What does this 32 mean? So actually here we use 32 kernels, right? And every kernel got a BIOS. So the number of BIOS equal to the number of kernels. So that is the meaning of this BIOS. We can have a look of this slide again. So every kernel got a BIOS. Every kernel got a BIOS. Here we got 2 kernels, W0 and W1. So we got 2 BIOS. And then we defined our weight and the BIOS. So what we're going to do is to do convolutional operation. So to do convolutional operation, we use tf.nm, the conven2d, convolutional in 2 dimensions, and the input is our input image, like 100 by 100 by 3. And the weights is conven1 weights, and here stride equal to 1, 1, 1, 1, also 4 dimensions, also 4 dimensions. So this first one actually represents the batch size. So here the first one means, for example, the batch size equal to 32. That means every time we will input 32 images into the model. So here the first one means we will do convolutional operation. We will do convolutional operation on every image. So if here this batch size, this one, we change this one to 2, that means for these 32 images, we will do convolutional operation every 2 images. And the second and the third one means the column and means the row and the column of the image. means the row and the column of the image all both equal to 1. And the third and the last one means the number of channels. The number of channels represent the number of channels in the image. So that is the meaning of the four ones. So actually in TensorFlow, if we are using CPU, the default data structure, we call it NHWC. So here N means the number of samples. So here the number of samples means batch size, and the H and W is a height and a width of the sample, and H is the channel of the sample. So that is these 4 ones mean. That is the meaning of these 4 ones. And here we are using padding equal to same. So the meaning of padding equal to same as we will pad, right? We will pad. And then I'm not identifying here. No, I'm not identifying the how many zeros we will pad around the image, but we use pad equal to same or pad equal to valid. If pad equal to same is, if pad equal to same means we will pad, and we will pad to make sure the size of the input image equal to the size of the output feature map. So that is pad equal to same. If pad equal to valid, means that we will not pad. So the size of the input image will be different from the size of the output feature map, maybe different. And that is convolutional operation. And the last step we're going to do is we do convolutional operation, and the next step is we will use the BIOS add. We will use a BIOS add to add the BIOS and come to add the BIOS, and then followed by a activation function we call a ReLU, and followed by the activation function we call a ReLU. So we use ReLU activation function. So the input of this convolutional layer is 100 by 100 by 3, and the output is 100 by 100 by 32. Why? What does this 100 by 100 by 32 mean? Or what do you think about? Yeah, yes, please.
Since we have 32 kernels, so we have 32 feature maps.
Yes, and 100 by 100. Why?
The size of the image.
Yeah, the size. Yeah, thank you so much. So here 100 by 100, the size of the input and the output keeps the same, because here we use padding equal to same. And this 32 means now we are using 32 kernels to extract a feature from the image. So we got 32 feature maps. So the next, the next part is we will use an max pool to add convolutional layer, followed by the first to add pooling layer, followed by the convolutional layer. So let's have a look. So for the max pooling layer, the input is the output of the first convolution layer, that is ReLU 1, right? And the kernel's size here is 1 by 2 by 2 by 1. So the first one and the last one indicates the number of samples and the number of shapes. So for TensorFlow, these first and the last always be 1, And for the feature map, the rows and the columns, the size of the pooling kernel, we use 2 by 2. And the strides equal to 2 by 2, and the padding equal to valid. So here, the output would be 50 by 50 by 32. Will be 50 by 50 by 32. Just like the example we've mentioned. Just like the example we've mentioned here. Wait a second. Just like the example here, the kernel size equal to 2 by 2 and the stride equal to 2 by 2. That means the column and the row would be reduced by half. So that is the output of the first convolution of the first pooling layer. So then for the third layer, also we add a convolution layer. Third layer, we also add a convolution layer, define our weights and the BIOS, and followed by convolutional operation at BIOS and through a ReLU function. So here we are using 64 kernels, and here we use padding equal to same, so the size would keep the same. And then we use a pooling layer. And also the kernel size equal to 2 by 2, strides equal to 2 by 2. And after this pooling layer, second pooling layer, the size reduced to 22 by 22 by 64. And then we add another convolutional layer. So the input size is 25 by 25 by 64. And here we use 128 kernels to do convolutional operations. So the number of output feature map should be 128. And the padding equal to same, so the size keeps the same. And then we add the third convolutional layer. So after this convolutional layer, the input size is 22 by 22 by 128. So the output would be 12 by 12 by 128 after the third pooling layer. So after the third pooling layer, we add the seventh layer. It's also a convolutional layer. And here we are using also 128 kernels. We are using 128 kernels and padding equal to same. So the output size will be 12 by 12 by 128. And here is our last pooling layer. So we reduced the size by half. So the output size will be 6 by 6 by 128. So that is the main architecture of this model. We use convolution layer followed by pooling layer four times. And then we will use fully connected layer. So first, after the fourth pooling layer, the output is 6 by 6 by 128. And so the first thing is that we're gonna reshape the matrix 6 by 6 by 128, this matrix into a vector. So here we're gonna reshape the input is the output after the fourth pooling layer, and the number, the dimension of this vector equal to 6 by 6 by 128. So after this operation, this becomes a vector. So becomes a vector that is 6 by 6 by 128 vector. And then we will add fully connected layer. So to reduce the dimensions of this reshaped So for fully connected layer, also fully connected layer got weights and BIOS, that is WX plus B. So here we define the FC1 weights and we define the FC1 BIOSes, and the input is reshaped is a vector, and that is X and W. We multiply X, W, that is W times X plus B plus BIOS, and through also a ReLU function, that is the first convolutional layer, that is the first fully connected layer, and that is the same for the second fully connected layer, weights and BIOS, and WX plus B through a ReLU function, and here we're gonna, if trainable equal to true, so if we are training the model, we will add a dropout. So dropout, the purpose of this dropout layer is to overcome the overfitting problem, is to make some of the neural states in this layer. So here 0.5, that means in the second fully connected layer, we will let 50% of the neurons are state neurons. And the last convolutional layer, the last fully connected layer also weights, and also we got weights and BIOS, also we got weights and BIOS WX plus B, and WX plus B, that is the final output, and we go back to have the view of the dimensions. So first, the output of the pooling layer is 6 by 6 by 122. So after the first fully connected layer, we reshape this to 1024 dimensions. We reshape this to 1024 dimensions, and the second fully connected layer reshape the 1024 dimensions to 512 dimensions, and the last fully connected layer reshape this 512 dimensions to 5 dimensions, and file represent the number of classes for this image classification problem. And then we can call this, function we've defined, that is the main structure, that is the structure of this neural networks. And we got input here. Input is placeholder, and this string equal to false. That means we will not, if string equal to false, that means we will not add dropout layer. And the regularizer is we are using L2 regularizer here, and we call this function and get the output. Output actually is a 5-dimensional vector, and then we input the 5-dimensional vectors through a softmax function. So it will map these 5 values into the probabilities. So that is the final output. And here we start the session. And we run global variables initializer. To initialize the variables in the model, and then we define the loss function. So here for the loss function, we use cross-entropy, softmax cross-entropy loss function, and the input of the loss function here is the logits. Logits is a prediction of the model, and the labels is the actual label. Sorry, the labels here. Why is the actual label? Here the labels is the actual label. and we compute the loss function, and then we define the optimizer. Here we are using add-on optimizer, and the learning rate for the initial learning rate equal to 0.001, and the aim of the optimizer is to minimize the loss function here, minimize the loss function here. And then let's have a look of this function. So this, we define a mini batch function. We define a mini batch function. The aim of the mini batch function is to randomly pick several samples from the data. If the batch size equal to 32, we will random pick 32 samples from the training data set. And here is the training process. Here is the training process, and we may focus on this. Oh, sorry. Here is a training process and some hyperparameters. For example, here, number of epochs. So what the epoch means that we will train the model for 3 times, not 3 times. That means we will train the model, use the whole training data set for 3 times. Just like when we learn something, we are allowed, or when we read the book, we are allowed to read the book for 3 times. That is the meaning of number of epochs. So here, the model are allowed to look at the images for 3 times. And here the batch size equal to 32. The batch size equal to 32. Here we also define the tf.train receiver to train the model, And so here the for loop, when the apple equal to 0, when the apple equal to 1, when the apple equal to 2. And first, the training loss and the training accuracy and the number of batch both equal to 0. And then we start the training, and we use mini batches, this function mini batches, to get a batch of data. So the batch size equal to 32 would get 32 samples from the training data set, and then that is X train and Y train. That is the X train and Y train, the images and its corresponding samples, and we use session the run. So we use session the run. First, we need to feed it, that is to feed the training samples into the input placeholder, and then we use Y train to, then we use this Y, and then we feed the actual label into the Y placeholder, and what we want to get is the loss accuracy. What we want to get actually is the loss and the accuracy and the train optimizers, and here the loss and accuracy for each batch size. And also it is the same for the validation set. It is the same for validation set. Finish the run and feed the samples and actual labels into the model, and get and finish the loss and the accuracy value, and we can have a look. And finally, after all 3 epochs, train the model, and we can have a look of the batch accuracy and the batch losses. That is the first epoch. We train the model for several batches. We train the model for several batches, and that is the train loss, train accuracy, validation loss, validation accuracy for the first epoch, and we can have a view the train accuracy is 0.38, and the validation accuracy is 0.56, and after second epoch, the train accuracy is 0.59, and after the third accuracy, after third epoch, the accuracy is 0.65. So that is a training process, and you can have a view of this data maybe after the class. So here the testing is a test process. So we load several data, 5 data. Here we load 5 data, and to restore the structure of the model, and also the weight information of this model, and to test these 5 images. So you can have view of this experiment after the class. So maybe Bilar needs some time so to talk about the end of the session. So one thing I need to mention is that yesterday I sent you guys an email. Wait a second. Oh my gosh. Yesterday I sent you guys an email, and here is a customer training survey. Here's a customer training survey. Here, this is a survey to judge our performance. So if you open the survey, you can wait a second. You can find several questions, maybe 7 questions to judge our performance, and these scores are very, very, very important to us. So the maximum, the full mark is 5, and also is a pass mark. So but it's very welcome that if you have any suggestion, please fill in the last of the 3 questions. You can give any other comments or suggestions, but be very patient to pay attention to the first 7 questions, and you need to mark our performance. No matter why you mark about the organization, or you mark about the training materials, or you mark about the communication. Everything you marked here are judging us, are judging me and my colleague. So this 7 question is very important to us. And if you have any comments, any suggestion, anything you want to complain, please you can complain here, and here. So that's all. There is a questionnaire, and it's welcome if you want to fill this questionnaire, fill this survey. You may spend 1 or 2 minutes. So that's all for this training session. So maybe Bilar sent me a message that yes, please.
Thank you, Kelsey. We have submitted a survey, and your presentation and instructions were very good. We really liked it. I just wanted to know, in the email attachment, we see 2 chapters in PDF, chapter 1 and chapter 2. Are they from a book, or they are Huawei material?
No. I've sent you guys maybe another 2 chapters. That is a neural network basics and the image processing applications. For the certification exam, you just ignore these two chapters. Ignore these 2 PDF, because I think these 2 PDF for you guys as the reference to better understand about the neural networks?
We have not received these 2 PDFs. We have received the survey. We have filled the survey.
Okay.
And yeah.
Oh, okay. Maybe after class, I will send these 2 PDFs to you guys again.
Okay. Thank you. Thank you very much.
Okay. Thank you.
And in case
yes,
I had one suggestion, we would really appreciate. We have received the labs, but are there any more labs that you would like to add other than the ones which are part of the lab manual in HCIA course, just for our practice?
You mean other labs? Maybe
Yeah.
After class, I will send the email to the local manager. Maybe some reference, some labs, some experiments from
Yes. Yes.
DTAP, and you can take some practice.
Thank you. Thank you very much. Thank you very much, Kelsey.
Okay. Okay. Thank you. And the last thing, please don't. The last thing, then the below asks that maybe you guys need to turn on your camera, and then we can take a picture.
Yeah, thank you so much, Kelsey, and thank you so much everyone for participating in this training. I hope you guys have had a great journey with Kelsey and our team. So we are working day and night during the pandemic and making sure that the learning never stops, which is our goal during this pandemic. So I hope everyone is having a great training sessions, and everyone I hope are conducting the online classes. So this is a very good example of making your online learning productive. So this is one of the case. I'll want everyone to turn on the camera, and then I'll take few questions or suggestions from your side. If you have any questions or if you have any suggestions for us to improve, because we are just trying to improve ourselves during this hard time. We are looking for great suggestions from the great teachers across Pakistan. I'll like to mention that after this training, everyone who have 80% of attendance are going to get a free certification voucher. So I'll be arranging that, and I'll be sharing. So it will be most probably after the Eid. After Eid, I'll be sharing you the one form which you guys have to feed back to me, and after that I'll be arranging vouchers for you, and I'll arrange a remote examination for you. So currently, during this pandemic, we have started a new we have developed a new features of the online examination, which was started in April. So that's the new feature that we are using for these remote examinations. Everyone will be getting an exam link, and you guys will be monitored through our AI based algorithms during the